find it to be an interesting one. We have David L. Sturges, who is a research forester with the Rocky Mountain Forest and Range Experiment Station here in Laramie. His schooling was from a good university, BS in Range Management from Utah State, as well as an MS in Range Management from Utah State. He works in the Watershed Management Research at Laramie with the station since 1962. Forest research effort at Laramie centered on the hydrologic characteristics of mountain bog areas in the Medicine Bow Mountains. Research since 1968 has centered on studies of the hydrologic characteristics of big sagebrush lands and the effects of land management practices on hydrologic characteristics as well as management of the blowing snow resource. Sturges has charge of the research program at the Stratton Sagebrush Hydrology Study Area located west of Saratoga, where Sagebrush Research Program is located. The snow fence study being discussed at this seminar was one of the land management practices tested on a watershed basis at the Stratton site. And if any of you are interested or know somebody that's interested in the Stratton site, they're going to be closing it down, they said, in a month. But it's been there for a long time. We hate to see them lose it and so forth, but I guess that comes with all the cutbacks. We looked for ways to try and come up with the money from the water center, but we just had, our budgets were too low too. So we feel badly about that. With that, I'd like to introduce Dave Sturges to you, who's going to talk on snow fencing to increase stream flow. Dave?
Well, thank you, Vic. It's good to be here. I hope we can share some things today and you'll gain a new appreciation for probably a water source you haven't much thought about in Wyoming. If we could have the lights now. Well, this is the snow that we don't want to talk about today, the nice fluffy stuff that kind of ends up on Christmas postcards. Our snow is snow in motion, and that's a product of a much more hostile environment, and one that's this type of motion is common on our rangeland areas where we have vast expanses of land exposed to the full force of the wind. The vegetation's short and it doesn't retain much of that snow on site. There's several features of our climate that bring about this kind of a phenomena. First of all, of course, the bulk of our precipitation does fall as snow. In the upper elevations of the sagebrush zone, upwards of 75% of the total precip comes as snow. As we go out into the eastern part of the state on the Great Plains, maybe half or more. So snow is a major input wherever we are in Wyoming. And then the temperatures are quite cold. Here we've shown some average monthly temperatures at the Stratton site, which is west of Saratoga, in comparison to a couple other locations in the Great Basin sagebrush country. And Wyoming's cold. So those temperatures able to hold the snow for 5-6 months. And then you superimpose our wind regime on top of these other two factors. Winds peak out during the winter months when the snow's coming, and we have that snow resource that's being moved about by the wind. And we're talking about huge quantities of water that are being moved by the wind. Here's one of the large accumulation areas for drifted snow. And in fact, it's the largest reported area where snow drifts melt seasonally anywhere in the world. You might find that surprising. Maybe think of Russia and Siberia as a place of huge quantities of drifting snow, or maybe the Alpine zone, but that's not true. It's right out here on our sagebrush rangelands, in this case, south of Rawlins. In a big year, that drift will be 60 feet deep. So I'd submit that blowing snow is certainly a resource that we haven't appreciated in the past, and along with the wind that produces that resource, there's two resources that are really haven't been tapped in Wyoming. The engineers have tried to capitalize on the wind resource and convert that wind power to generator into electricity using these large wind generators, but so far they just haven't had much luck. None of those efforts have really been successful on a routine operational basis. Well, we feel with our watershed research here in Laramie that we have provided some useful tools to get a handle on this blowing snow resource. Before we actually get into the study that Vic talked about, I'd like to talk about some concepts that go along with blowing snow. And the first concept is that those little snow particles, once they begin to move along by the wind, don't move endlessly. The first thing that happens is, of course, the points on the flakes get broken off, but as they're tumbled along, they're losing water continuously by evaporation. And that's true even though the temperatures can be many degrees below freezing. And that evaporation rate is surprisingly rapid. That little hypothetical particle up there at the top travels about 2 miles before it completely evaporates. So think about that, 2 miles. And all of the water in that snowflake has gone back to the atmosphere. And if you don't kick anything away today more than that, my efforts will have been successful. Well, if you stop to think about that, somehow it's got to be true. Or why, for example, isn't Cheyenne being buried by tens of feet of snow that's coming off the Sherman flank? Well, it's because that water in those snow particles goes back to the atmosphere. So that's been termed the maximum transport distance on our diagram. If we're interested in estimating the quantity of blowing snow arriving at some locations, since this is a snow fence that's we put there on the diagram, the transport distance may be limited. We need to know the actual fetch distance that contributes that snow. And as on here, a grove of trees, for example, might form a barrier that defines the upwind distance, that contributing distance. Maybe it could be a deep ravine that acts as a natural trap that stores all the incoming snow. So we have a contributing distance to our point of interest. And then, of course, we've got to have the snow. And not all the snow that falls in the winter forms our blowing snow resource. Part of that snow will be trapped by the vegetation. Part of it's going to be held in the little irregularities in the terrain. And when we get some of our warm days in the winter, maybe part of that actually will melt. So only that part of the winter snowfall, only that water that's actually relocated by the wind becomes our blowing snow resource. Well, all of these ideas have been put together, incorporated into this relationship, which enables us to estimate the quantity of blowing snow arriving at any location based on these features that we've talked about. And this type of relationship then forms the basis for the scientific snow management practices. Okay, let's move on here. The snow that accumulates in the drifts, of course, can be a source of water, and people have long schemed about ways to use that water in the snowdrifts. So we'll be talking now for the rest of the time about this snow fence watershed study that was conducted at the Stratton Sagebrush Hydrology Study Site. That area is located west of Saratoga, out on the windswept sagebrush rangelands. And through the years, we've been looking at the various hydrologic effects of different land management practices imposed on sagebrush. And the approach taken for a lot of those studies was on an entire drainage basin, not just some plot study looking at a small area, but what's the cumulative effects of these practices on the entire drainage basin. Out there on the Stratton site, there's 3 main watersheds. 2 of them have perennial flow, Sane Creek and Loco Creek. So that's pretty unusual in the sagebrush type itself to find the drainages that do flow year-round. And then the North Draw watershed flows just in response to snowmelt in the spring months. North Draw was selected for the fencing treatment, and the Loco Creek watershed is served as the untreated pair, so to speak, of this study approach that we have, utilizing what's known as a paired watershed study. And that involves obtaining your water measurements for a number of years from the 2 drainages when they're untreated, until finally you're able to predict the flow on one watershed from the flow on the other one at a given level of statistical precision. And once this pre-treatment calibration, as it's called, has been achieved, then you can go ahead and put a treatment on one watershed. You go ahead and measure what happens, and from the information collected on your second one, which remains undisturbed, you can estimate what, in this case, say the water flow should have been. You measure what actually happened, and then that way provides you a way of assessing just what the treatment has done, even though the climatic conditions we know range widely from year to year. So the paired watershed approach. Loco Creek served as the untreated watershed, and then North Draw was snow fenced. And we just used that portion of the flow on Loco Creek, the snowmelt runoff portion, to match with our snowmelt runoff on the North Draw watershed. The stream flow was measured at this type of a gauging station, which involved 120-degree V-notch weir blade, where the water measurement was made, a stilling pond behind that. And then that weir blade sits in a cutoff wall that forces the subsurface and surface flow through your measurement section. Our case, the cutoff walls went down 10 feet or so down to some pretty solid material. Well, out there on Stratton, we are in a major snow relocation area. The creeks, of course, are down in the bottom of the draws, the site of the natural snow drifts, and so it was necessary to protect that gauging station with a monoplate arch. Here's the Loco Creek gauging station. Notice the little door there on the end that provides access down to the stream gauge in the winter months. And then later on in the winter, or not a big winter in this case, that entire drainage basin has been filled by the drifted snow, and we're having to dig down just to get to our access door down into the gauging site. So that's the Loco Creek. And then Sane Creek, picture that installation before any treatment had been imposed in the summer months. Everything protected there under the monoplate arch as well. Well, our gauging stations provided the information about a continuous record of water flow. All that information was recorded on a chart. We were also interested in sediment movement from these watersheds. At North Draw, when we visited the site on our service visits, we collected a sample there at the V-notch for suspended sediment levels in the water. And then the year before the fence treatment was installed, we put in a pumping sediment sampler to take samples when we weren't there. So give us a better record of sediment in our water. And we routinely collected a sediment sample at 6 o'clock in the morning, 6 o'clock in the evening, twice a day. And these times corresponded with the low points in the daily snowmelt cycle, and then when the runoff was at its daily peak. Those samplers gave us an indication of suspended sediment levels. The larger particles, though, would settle out in the stilling basins behind the V-notch weirs. And that bedload deposition, as it's known, was measured annually with a rod and level survey. Well, snow accumulation was another parameter that we were very interested in. And when that work began at the Stratton site more than 20 years ago now, we immediately installed index transects across the major topographic catchment zones, and then took measurements of snow deposition in these zones annually at the time of maximum accumulation. So that then we have a record through the years of snow accumulation in these topographic areas under a wide range of the climatic conditions. When it began to look like we would put in the snow fence treatment on North Draw, we put in 7 additional long transects, shown by those longer black lines, on the area of the watershed that was to be treated. And the snow data on these transects enable us to actually quantify snow deposition and, in turn, snow water content in the lower portion of the watershed there. There's one other feature, that lower part of the North Draw watershed was the area that was fenced. At the same time the snow fence was built, we built another stream gauge immediately ahead of that fenced portion of the watershed so that we could separate out the water coming from the upper part of the drainage from the total flow, be able to get a better handle on how much was actually being contributed by the treated section. And here we have an aerial view of that North Draw watershed. The stream gauge, the outlet gauge is in the upper or the lower right part of the photo with the road leading to it. We had a fairly deeply incised channel extending about a half a mile above the gauge. And then in the upper part of the watershed, it opened up and became pretty flat. And that area didn't accumulate appreciable quantities of snow. So this lower section then was the part that was treated. Local creek drainage is coming down there in the greener area at the bottom of the photo. The stream gauge would have been located on further upstream off to the left of the photo on the part of the local creek drainage that was actually where we were doing our water measurements. Well, the stream flow at North Draw originated primarily from the snow that was deposited in this incised channel reach. Most of the water came from that incised channel. And that channel was a pretty efficient trap early in the winter before it filled. But once it reached this stage here, as it's just about to fill, it became a very inefficient trap. And the incoming snow then would simply blow on by. And what we had was those deeper part of the draw filled in with snow, smooth concave surface, and then that would enable the snow to blow on by. So our treatment was designed to enhance the natural storage capacity of the incised channel reach. And we felt by doing this that would be the optimum treatment in terms of getting the highest water delivery efficiency from our deposited snow that we could. Here's a picture, aerial picture, just as the fence was being built. And we went ahead and made our estimates of snow transport arriving at the North Draw location. And based on that, we were able to design a prescribed snow fence height. We were able to put in or identify a location where that fence would do everything that we wanted it to do. And so what we ended up with was a fence being located about 10 times its height upwind from the channel. And based on the snow transport in an average year, that would put the drift about to the channel center line. And then that, of course, provided additional capacity was there for the years with above average precipitation. So that this fence treatment then was located such as to maximize delivery efficiency, to provide a very high efficiency in terms of catching the blowing snow arriving there, even in years with a very high precipitation. The fence itself was what's known as a Wyoming snow fence. And that design was developed here in the state by the Highway Department. And they needed an efficient snow fence when the state got into a big program of building snow fences along the highways to provide protection from drifting snow. Our fence is 12 and a half feet tall, and that's a common height that you see out along the state highways. And it was built under contract by an outfit out of Rawlins. They constructed the panels at their shop in Rawlins and then hauled them out to the site and lifted them in place with a crane. Attached the rear members there that supported the panels. The entire fence is made from rough cut lumber. The support pieces in the back are all 2x6 rough cut lumber that's been treated, so we won't have rot where it's in contact with the soil. And these fences have a projected life of at least 25 years lifespan. The panels themselves, the part that face the wind, are comprised of 6-inch wide boards that alternate with a 6-inch gap. So then you end up with about a 50% solid area and 50% open. And that's the optimum configuration for a snow fence in terms of doing the best job of trapping blowing snow. Each panel is 16 feet long, 12 and a half feet tall, as I said. The fence there on North Draw had a total length of about half a mile. Well, that fence was built in the summer of 1983 after a 10-year calibration period when we were measuring stream flow on North Draw and on Local Creek, both of them in the undisturbed condition. If you were around Wyoming in the 83-84 winter, you'll probably remember it. It's the last big winter we had, and it was the winter when the antelope really, we had the big die-off because of so much snow that they couldn't paw down through the snowpack to reach the feed. This is the picture on November 29th, 1983. We already had a fair amount of snow there. The drift's beginning to build. And then 2 days later, when get some strong winds and a lot of blowing snow, and that fence is really doing its thing, just packing the snow in there. Just a few shots now of the drift there. It really is impressive from the ground. Here's our thiacol going down the channel bottom as the drift's creeping out over the channel. Walking down there on the channel, you can see those big wall of snow coming out. Impressive from the air. This is a 1985 picture, which was a winter with average precipitation on towards, not quite to the time of maximum snow accumulation, but the drift was quite large there. It's pretty much out over the channel center line, and we're holding oh gosh, 25 feet of snow or so there at the deepest point. If you notice clear up the top part of the picture, there's a little scour hole. That's where the stream gauge at the upper part, just above the fence, was located. That was a flume where we were measuring the water coming off the upland area of the North Draw watershed. Well, our snow measurements on our transects indicated that we really did do big things in the way of changing snow accumulation. We can take a kind of a look at that in diagram form now on one of our permanent transects that just crossed the immediate channel reach, showing 1983, 1985, 83 being before the fence was built, and then 85 after fence construction. Both those winters were years of average precipitation. The yellow there with the 83 data shows that smooth concave surface. And once you reach this type of a snow deposition, and there's a little additional snow that accumulates because the wind has a smooth surface and it just moves on off. But with the fence there in place, we were trapping all the snow that was arriving at it, so we ended up with a bigger drift. 85 was an average winter, so that we still had ample capacity left to store snow for big years. A little different look at our data now. This is some regression relationships in pretreatment years shown by the green between snow accumulation on our unfenced watershed, Local Creek, and on the North Draw watershed years before the fence was in place. And then the orange line indicates the relationship there in years after the fence had been constructed. All of these differences in terms of snow accumulation, water yield characteristics are all highly significant from a statistical standpoint. This kind of a plot indicates that, boy, the rate of snow accumulation has really changed with that fence treatment. Early in the year, there's not much difference between the two, say when we have less than 50 feet of cross-sectional area on that transect, and that's the time that the snow is filling the sagebrush up. That's the time before we get much transport. But once we move on into the main transport season, then the rate of accumulation was much faster after the fence treatment was in place. This was kind of surprising. Down there in the lower part of that plot, we'd always thought that the channel was pretty efficient trap, but this kind of data indicates that even before it filled, it wasn't near as efficient as it is now with the fence system in place. Well, if you don't like this kind of data, we can put these results in a little more form that's easily understood. Represented by our snowmen before and after fencing and an average treatment effect. If we take that entire channel reach that's been influenced by the snow fence, we've increased the water content in the snow there by 85% with that fence in place as compared to before the fence treatment. Well, we put that much more snow in, and you think, well, that's got to make a lot of difference in terms of actual water yield, and indeed that's the case. Here's now the plots for our snowmelt runoff on the two drainages, Local and North Draw, expressed in centimeters of water over the entire drainage area before and after fencing. And what we did in terms of water yield was to increase runoff 137%. We said we increased snow 85%, runoff 137%. So that indicates that the additional snow that we deposited there with the fence was coming off with quite a high delivery efficiency. And that's what we'd hoped for with our treatment, that we could, by locating the snow over the channel, we could increase the runoff efficiency on the additional snow. Okay, looking at that same data a little differently now, for every bottle of water that we had before treatment, after treatment we have that same bottle plus 1 1/4 additional bottles of water. 127% increase in water yield. So we've changed the total quantity of water coming off those drainages. We've done some pretty dramatic things too to the length of the runoff on the North Draw watershed, the runoff duration, the number of days of flow. Those are the two relationships before and after treatment. What we did was prolong runoff on North Draw by 33 days. Half of that longer runoff period came at the start of the runoff season. Half of it came at the end of the runoff season. Of that 33-day period, I said that we prolonged runoff. Here we're just looking now at the Julian date that the snowmelt runoff ends. And so we're getting runoff in June, early July, depending on the year, for 2.5 weeks more than we had without that fence. If you're a downstream water irrigator that's depending on direct flow, then that becomes very important to you. You've got water in the creek that you can divert out to your irrigation. If you're a fisheries manager, that additional water during the summer months is important. It improves the habitat for the fish. And a little different way of looking at that same result now, before treatment on North Draw, runoff began on the average about April 26th, and we had surface flow through June 9th. Now with the fence in place, we're starting flow April 3rd, and we're ending it June 26th. So we did have some pretty dramatic changes in terms of snow accumulation, in terms of water yield, in terms of when that snow melts, and we're getting surface flow. That fence treatment didn't change anything at all in terms of sediment movement. The water coming off of the North Draw watershed, just extremely high quality. Even before treatment, it compares very favorably with any mountain watershed in terms of sediment content. We can look at that data. Here we've plotted stream average daily flow, stream flow, and average daily sediment content, the solid line. And again, some information from '83, before any fence had been built, a year with average precipitation. Most of the days during that we had snow melt, we were running less than 10 milligrams per liter suspended sediment levels. We've taken a look at that, even that small quantity of material in the water, and half of that is simply organic matter, little pieces of litter that the water picks up. So very little soil movement coming off of these watersheds. 85 now, after the fence in place, again, just virtually nil, less than 10 milligrams per liter on all but a few days. The solid black line now, another indication of what that fence has done in terms of flow regime. Had the fence not been built there, the runoff would have ended where that solid line is, the black line. Instead, we've carried the flow on pretty much through all of June with the fence in place because of the additional water there. And if you take a look up the North Draw channel, it's kind of helps explain why we don't have much sediment movement. It's just densely vegetated with herbaceous material, so that all of that then acts as a trap, removing the silt and particles and clay particles, sand particles, and depositing it, retaining it right in the channel reach. And the other thing about these deep snow drifts is that their rate of snow melt is limited by the energy input. there's only so much energy available for melt. We have that drift on a relatively small area, so we don't generate a lot of runoff from these drifts that create real high peaks. Well, people are always interested about the economics of this kind of a water improvement practice. They want to know how much it costs. And I'll ask you a question. What are you willing to pay for water? If you're buying it at 35 cents a gallon out of this aqua vend machine, you're paying $114,000 an acre foot. And if you're like this guy and forget to put in your bottle and it runs out on the cement, you're paying way more than $114,000 an acre foot. Well, certainly the cost of the water with the snow fencing treatment is not going to be anywhere near that price that 35 cents a gallon. We haven't done all the economic analysis yet, but we do have some preliminary figures just to pay back the cost of building the fence based on the 25-year life expectancy for the fence. Based on our average increase in stream flow, you're going to have to get about $95 an acre foot for that water to pay for the cost of the fence installation. Now, that's certainly not water that lets you irrigate a hay crop, but it's water that might be competitive when you begin to get into an industrial use or you don't have any water from any other source, and you can begin to put out some money. Well, the North Draw study is the first effort anywhere that's been able to quantify water yield increases through snow fencing. And that's not to say that it's been the first watershed study. There's been several others conducted in the past, but none of them were successful in demonstrating that you could increase stream flow using snow fences. So I'd like to leave you with the reasons why that study has been so successful. First of all, the fence system was designed using some scientific criteria. And then second, the drift was located over the existing channel snow so that we maximized the water delivery efficiency. And then thirdly, the soil conditions, the geologic conditions here at this North Draw site were such that we were able to carry that water, the surface flow off the drainage, have it come down and flow out of the watershed so that we could measure it. And each of those ingredients is essential for any snow management project to be successful.
Questions?
Sure.
Your runoff started sooner in the season. Why?
Well, not all that snow behind the fence was 20 feet deep. As you got out towards the end, it was shallower. And before we get any runoff on that North Draw watershed, we have to recharge the groundwater system. There's a groundwater table there that has to come up, and then you begin to have surface flow. And so we had additional snow in that channel reach. Part of it was shallow, and it was melting and recharging that groundwater earlier than occurred before the fence was there.
Do you feel there was any downwind negative effect from removing the snow that might have gone there, or is that not true because the snow would have evaporated into the atmosphere before it got there?
Yeah, well, this particular site, there's nothing downwind for, geez, 10, 15 miles. Yeah, by putting that snow fence there, we've done two things. We've trapped any snow that was drifting and holding it in place. So if somebody was immediately downwind of this site and was depending on that snow, they might feel they'd been robbed. But we've also created some new water in the sense that we've trapped snow that would have drifted downwind anyway and evaporated, and nobody would have gotten any good out of it. So we've redistributed the snow with the fence, and then we've also created new water by not having the evaporation losses.
Yeah, Dave, you mentioned those fences were what, 16 feet high?
These were 12 and a half feet tall.
Okay. Is there an optimum height? In other words, could you, if you built it 100 feet, would you get proportionally that much more increase?
Well, the drift size is going to be limited by the quantity of blowing snow arriving at any location. So you could build a very tall fence, but you'd never have enough snow to fill it. Some of the highest transport areas in the world are right out here along I-80. And that country we're working with, they're west of Saratoga. And there's hardly, well, probably with two 12-foot fences, you could store the snow flux anywhere in the world, I dare say. And that's because of these evaporation losses. We're limited on the distance upwind that the snow reaches the site because it evaporates. And until, well, that one formula I put up there lets us estimate the transport at any location. And until this relationship was developed, until these concepts were developed here in Laramie Watershed Project, largely by Ron Tabler. But until that information became available, there was no way to estimate in the past what sort of a fence system we needed. There was no way to estimate the quantity of blowing snow. So people, in effect, were maybe putting a small snow fence in on the Colorado River, and then when it didn't hold the transport, snow fencing was getting a bad name because it didn't work. So it's, you know, it's analogous to damming up a river. You've got to have, to hold the total year's flow, you've got to have a reservoir big enough to handle all that water. We've got to have a snow fence big enough to handle all the water. But if we build too big of a fence and we don't have the influx of snow, then we're only using a small part of the capacity of the fence system.
How much did your peak increase? Or did it increase very much?
We did another thing on that study. These intermediate drainages are really interesting from a hydrology standpoint. When you pack in that dense snow and you get a lot of melt suddenly from the upland areas, that water comes down, there's nowhere for it to go under the pack. And eventually you can build a water table up in that dense snow and have over the snow flow, we call it, eroding a channel in the snowpack, just like you have a creek bed. Well, we knew we were going to put in that additional snow, and we knew that the drainage was clogged anyway beforehand, and so we put in that plastic 6-inch plastic tube under the pack, and that's affected the peak rates early in the year, because now with that plastic drain pipe in there, we have a channel. It's there immediately to carry the water off before it has a chance to erode away naturally and create a channel. But no, we can't really directly assess it because we've changed some of the flow characteristics. But the years with high peak flows are the years when we get a sudden warming and all the shallow upland snow melts. But the energy, like I said, limits the melt rate from that drift. And the drift covers a fairly small area of the total watershed, so we don't generate that high of flow peak flow rates off of those large drifts. Brought over some snow fence models. It's always kind of interesting. As you go around the state, you see all kinds of fences, and the fence design has gone through a lot of evolution over the years. These are replicas of what we call the corn crib fence, or the 4-foot vertical slat Canadian type of snow fence. Farmers use it sometimes around their corn cribs, or people will put it up. You can buy it in 50-foot rolls. And Wyoming had quite a bit of early snow fencing. And you still see this type of fence around the state. Some locations along the highways, it's known as the Swedish snow fence, a very old design that came from the Scandinavian countries. And you get back, and it just kind of appeared. It began to be used. No sudden research development effort to come up with this design. It just evolved through the years, and it came over to this country, and because I guess it was used in Europe, then it got used in this country. It's got this recurved top, as it's called. No benefit in terms of snow storage, and these fences are usually about 6 feet tall. The kind you see out along the highways. The UP has some of this Swedish type of snow fence too. And then in about early 70s, the Wyoming Highway Department began to get into snow fencing in terms of road snow control. And we knew these Swedish fence wasn't much good. We knew this short Canadian type of fencing wasn't much good, and so there was an effort to develop a better snow fence that would store much larger quantities of snow than these shorter types of fencing. And that's when the Wyoming snow fence design was developed, 1972, 73 or so. And it was first built in 2 different heights. One of them was 12.5 feet tall, like we used on our Stratton site. And then it could be built in 6, 8, 10, 12-foot heights. Most of the early Wyoming snow fence was either 12.5 feet tall, or 8 feet tall. Here, just in the last few years, these designs been revised a little bit. And now they're building the same design in a fence that's 14 feet tall. And that 14-foot fence will store 25% more snow than the 12.5-foot fence, and it costs less to construct through some design changes. So that's made the cost per unit of snow storage even more competitive now with the taller fence. Looks like our time's about up, Vic.
Okay, thank you, Dave. We appreciate it. Before you leave, I also noticed